All right. So I'm going to talk a little bit about the future web, HTTP3 and Rust. I talked about something like this last year at RustFest, and this is sort of an update and a more maybe webby version of that talk. So first a little bit about me. I guess Hugo already said the most important things. So you can find more if you like. Yeah. So let's start with HTTP3. Who knows that HTTP3 is coming already? And how many of you are already using HTTP2 for your websites? Yeah, that's good. So yeah, even though many people do not use HTTP2 yet, so we're already looking at HTTP3, and it's coming down the pike later this year. And I want to start by talking a little bit about why large companies on the internet are working on HTTP3, why they started that work, and kind of what it looks like. And then I'm also talking a little bit about the Rust implementation of QUIC and HTTP3 that I have been working on along with some other people. So in HTTP3 is HTTP2 basically reformulated on top of QUIC. And QUIC is the Quick UDP Internet Connection Protocol. And that's basically a sort of updated TCP protocol with the latest, all that knowledge that we've gotten from widely deploying TCP over the past decades. And really, it turns out that there are a lot of things that we would do different if we would build it these days. So that's what QUIC is. And it started at Google, similar to what eventually became HTTP2. They deployed it for their servers and their Chrome browser. So if you're using Chrome against Google servers, you're already using a version of QUIC today, most likely. But that's a different version. So at some point, it moved to the IETF working group, and the protocol started changing from what Google was doing. Eventually, Google will be catching up with the IETF version of the latest drafts that are turning out now. So yeah, I still have November 2018 here, but that was old information. It turns out when they had some ideas about changing how a quick interface with TLS, and that required major rework. And if you're going to change OpenSSL and other TLS libraries, turns out that sets you back a few months. So hopefully later this year we'll have QUIC and HTTP3. So this is kind of the ideas of what I will be talking about. First, I have an animation to demonstrate the issue of head-of-line blocking. Any of you familiar with what head-of-line blocking is? Good. So what you see here is packets flowing through the network, from the application layer through the transport layer to the physical network. And in TCP, at some point, if a packet gets lost, then the other packets that come after it will sit on the transport layer, waiting to be delivered to the application until the lost packet is also delivered, because TCP means a reliable in-order delivery of your packets. There's just a single byte stream. And of course, that means increased latency compared to what's actually there on the other side. Because if you already have many of the packets, then it would be nice if you can deliver some of them. And some of them might actually be independent of the lost packet. For example, in HTTP, you often are pipelining multiple requests. So you have your index.html, and maybe you lost some packet there. But you already know that you want to fetch the style sheets and some fonts and some JavaScript files. And you could deliver those to the application, even though you cannot completely deliver the HTML yet. So this is sort of the basic issue that TCP has, and that even with HTTP2, which already does multiple streams over a single TCP stream, you cannot solve. There are facilities to do multiple streams over HTTP, over one connection in HTTP2, but this is where it still falls down. And this is what QUIC sets out to fix. So that means minimizing latency so that these kinds of issues don't happen. Also to improve the connection setup latency. It does multiplexing, so any socket can provide any number of connections. You can, I think you can use, they use explicit connection IDs per socket. So I think they range from 0 bytes to 18 bytes. And they can also be 3 to 17 bytes, but not 1 or 2 bytes. So there are a lot of options. You can have many, many different connections ongoing at the same time. But they didn't want to rip out kernels, basically. So they said, we're not going to do, because they also learned from like SCTP, other protocols that attempted to replace TCP in the past, and it turns out it's not actually practical. We cannot replace all those kernels, and rolling that out to the world is a pain in the ass. So what did they do? They used UDP. In UDP, you basically have a very limited framing on top of IP packets, and so you can use that. In some firewalls, it's going to be blocked, but they figured it's not too bad, and if more people start using it, firewalls will be forced to open it up. So the same as what we have where HTTP 80 is reliably open, that will hopefully also work here. So only the path endpoint can be affected. All the infrastructure is the same, it's just UDP, and it's usually deployed in user space. All right, you're not, also because they want to keep changing. That's the last point here, rapid distributed development and testing. They don't want it to gel in the kernel so that it's hard to update. If it's in your application, then you can easily move along to newer revisions of QUIC, adopting newer features. There's good support for connection migration. This is really common these days. If you have your mobile device and you walk to a different access point or a different cell tower, it would really be nice if you don't have to go through that painful connection setup again, and the TLS handshake and all that stuff that has to work with that. So instead, there's connection migration. There's really good privacy defenses in there, so that if you go to a different tuple, so a different IP address or port, then you will also change the connection ID. It will be agreed in advance over your encrypted connection. So the connection ID, which is the one thing that's sort of visible about your connection, will not be, they cannot correlate sort of your pre-connection migration and post-connection migration IDs. And it's always secure. I mean, we learned from TLS being optional in TCP. Of course, it came much later, but we learned that that's not the best solution. We sort of have the naive expectation that our protocols are secure by default, and let's bake that into the protocol from the start so that it's always there. And this uses TLS 1.3, so we get all the benefits of that, which is also quite nice. That means faster handshakes. It means many fewer cipher suites to do, and it's always authenticated encryption with associated data. Yeah, and so expect more, because people are already talking about QUIC v2. It probably in 2020 we will have QUIC v2. So it will keep moving. These large companies, the Googles, the Facebooks, the Microsofts, and the browser vendors, they're all on board. They want to move faster, or they want to keep applying their sort of development resources, development capacity to make all your devices and all your stuff run more efficiently and your networks. So QUIC is a sort of a modular standard. It's split up in a number of smaller documents. The invariants, document is sort of where it starts. It documents the things that cannot change from one version of QUIC to another. So that starts with, for example, how the basic header of the initial packet looks like, because that's where, if you want to be compatible, you have to have some sort of recognition that this is an initial packet, and you can go from there and upgrade to higher versions. Also, how connection IDs work is specified in invariants. Then transport, that's sort of the core part of QUIC. This is where all the stuff is about control flow, connection windows, streams, all that stuff. I'll explain more about it. Recovery, so loss detection, congestion control, that's where packets get lost. How do you handle that? It's quite different than in TCP, more efficient and easier to detect. TLS, so it's not just simple, because in TCP it's sort of TLS operates on a level above TCP, and then you go through TLS, but that's not the case for QUIC. In QUIC you have sort of a protocol that provides a handshake, a way of doing handshakes, and then over the course of your connection you just use the key material provided to encrypt the data packets and sometimes upgrade the keys, update the keys. Then in terms of HTTP, there's header compression similar to in HTTP2. We have HPAC. They called it QPAC. Maybe it may change to H3PAC or whatever, but it's the same thing. It's a similar way to doing header compression, but it's slightly changed to match the way QUIC works and make it more efficient again and more resilient. And then HTTP maps HTTP2 frames to QUIC. So this is also quite nice, because if you're doing your own if you want to build your own protocol, then you can really take some of these parts and reuse them. And so, for example, we're already seeing that, for example, there's DNS over QUIC is being talked about. So you may have heard of DNS over HTTP that people are starting to deploy. DNS over QUIC is being worked on. So things like WebRTC, the conferencing protocols stack is also looking at QUIC. And so using this stack, even if you want to build your own stuff, then can be quite useful to steal stuff. So streams. In QUIC, everything goes over streams. So from the moment you've completed your handshake, or even in some sense before that, you can start using streams. And what a stream is, there are 4 different types of streams. A stream can be initiated either by the client or by the server, and it can be unidirectional or bidirectional. And early on in the connection, you can configure how you expect your counterparty to behave. So how many streams they can open before you acknowledge them. So that provides some leeway. So for small clients, for embedded clients, you can say, don't open a lot of stuff, or don't open anything until I say so. Or for big servers, you can say, whatever, give me everything you've got. And all that happens through streams. A stream is basically saying, this is this in-order reliable delivery of bytes. And that happens then per stream ID. And how it works is that you get a stream frame in a QUIC packet. And it will just be the frame ID and the frame offset. So where does it start in your stream? And then you get some bytes. And the application can then decide to deliver that fully in order. Or also you can, if the application supports it, you can say, maybe we deliver some of these streams out of order because it's more efficient, and it's a big file that we're writing to disk anyway. We don't mind if it's a little out of order, and it's more efficient. So everything is streams. Recovery. So where TCP basically, you have sequence numbers, but the sequence numbers actually count the bytes on the stream. And that's, well, it can be quite confusing if you're doing retransmits. In QUIC, it's much simpler. There are packet numbers, and packets are numbered in the order they are transmitted. So that's simple. And then if you notice that one gets lost, then you send an ACK frame to your peer and say, well, this packet was lost, and it will resend you all the necessary frames that it still wants you to have. There's no reneging, so in TCP, actually you can say, I received it. Oh no, I didn't receive it after all. So in that way, you have to reserve more memory, or you have to keep larger buffers just to satisfy the use case that your peer may say, oh, maybe I didn't save it after all. So that's nice not to have to do. There's a really efficient way of expressing ACK ranges, so you can sort of collapse blocks of ACKs and then say, these ACKs I received, these ACKs I didn't receive, and do that with arbitrary depth and complexity in an efficient way. And there's explicit correction for delayed acknowledgements. So this was another problem with TCP, and benefit of hindsight is that these sort of things are now laid down in the specifications and can be tested to work. There's also support, which is actually not implemented very reliably before, but there's support for explicit congestion notification. So QUIC stacks are expected to set the required bits in IP packets. That's actually a little complex because, for example, your Rust user space networking protocol or APIs don't support that. But in our implementation, for example, we do have a little unstable Rust code that can do this by talking to libc. And that can make it easier to do earlier detection of network problems. So TLS, at some point it was just stream 0 is reserved for the TLS handshake, but they figured out a way to make it more efficient and more secure. So what instead they're now doing, there's a reserved crypto frame, and that's always used for handshake data. And instead of exchanging TLS records that then contain TLS messages or handshake messages, they now change it so that we're directly exchanging handshake messages. Now, as you might expect, as I mentioned earlier, if you want to change your TLS stack, your OpenSSL or your secure transport or your whatever Windows got, that's a bunch of work. So the really nice thing is that we are using Russell's, the fully Rust native TLS stack. And there it's really much easier to make these sorts of changes. So as part of implementing our QUIC stuff, we also took care of doing Russell's and implemented full support for everything that's needed in QUIC. And actually that's a really simple API that I'll show you later that you can wrap around that. There's a little TLS extension that's used for these sort of transport parameters. Like I mentioned earlier, how many streams can you open? What sort of idle timeout should I expect? A few other things like that. And then after the handshake, we don't use TLS anymore. We just use the secrets that we got from the handshake and use them directly. And every once in a while, it will be updated when either peer requests it. And then we got HTTP3. So that's an application level protocol negotiation string. Well, it's not actually a string, it's a set of bytes, a byte sequence, which is negotiated during the TLS handshake. And again, it's very similar to HTTP2 because, of course, we already went through the trouble of learning from HTTP 1.1 and putting everything we learned from that in HTTP2, 5 years or 10 years ago. But there are some small differences here. And some This is really the part of the standard that's also not gotten a lot of testing yet, because everyone's been focused on QUIC base layer so far. So this is also where we expect more change might still happen. So, and then what you get is this. So what you see here is interoperability testing, where you have a bunch of clients here. So this is Quinn, that's our implementation. Here's Apple, here's Nginx. Here is ATS and F5, this is Windows. Then there's Facebook, it's called Move Fast. Well, and so a bunch of other, and a bunch of server implementations, and you see all these sort of quick features that they already successfully tested to work. And this is how we track the status of implementations and how interoperable we are. And actually, Quinn is doing pretty well here, although we haven't got much HTTP3 support. So that's still an ongoing project. Any questions so far? Good. So then moving on to the Rust part, because that's what we're all here for after all. So last year I started an implementation just from scratch. I proposed this RustFest talk, and so I figured if I get that, I will write an implementation. That was a little bit hubris, but you know how it goes. A little hubris can go a long way. So today we do have a working implementation, but the lucky part was that another guy had also started an implementation, actually slightly before me, but he hadn't written it up on the wiki yet. So late last year we merged our implementations. We sort of folded all the good stuff from both, and that was a really, really nice working together. It's much easier to stay motivated as well, and we could review each other's code, so that also really helps. And actually, by the end of 2018, when the newest draft came out, we were one of the first ones to really be conforming, and that's pretty good, I think, when you're competing with the likes of Apple and Windows and stuff. So today you can already get the 0.2 release from Crates.io, which implements, I think, draft 17, which is now a little stale, but still pretty good and functional. And of course, there will be future releases. So where we started out is to say, of course, we need to implement these specifications faithfully. We want a correct implementation. That's really important in these sorts of low-level things. And that's why we have all the interoperability testing. But we also want to make sure that we write idiomatic Rust, well-typed Rust, performant Rust ideally. So we have a futures-based architecture eventually. And we use the type system. We have a lot of enums and traits. It all works quite well. And we have currently pretty okay test coverage. It's not stellar maybe, but it works good. And I think it's again that 2 volunteers in their spare time can make this tick against the large players speaks for Rust as well, in my opinion. So here's sort of an architectural overview. We've split it into what's currently 3 crates. So really the meat of it is here. But this is actually not, there's no futures here. It's just simple, straight Rust codes, deterministic blocking protocol logic. And that's really the start point. And it could also be the basis for a C API, for example, if you want to use it in something else. So really it's the endpoint is really sort of where you would slot in a socket, because there's also no networking in here. It's just processing incoming datagrams and then going through the motions and offering an API for extracting the stream data. So there's an endpoint there that takes care of doing all the connection ID stuff and dispatching from the incoming datagrams to the right connection. And there's a pretty big connection type that takes care of all the per connection protocol logic. There's packet encoding, decoding, crypto stuff that uses Russell's and the ring cryptography stuff. There's even in ring there's now a particular code to support QUIC header protection. So QUIC not only now protects the data, but also protects parts of the header that are sensitive. And that's because it's a kind of a particular use of stream encryption. The ring maintainer didn't really want to offer a generic API for that, but he offered a specific API to support that, which is really nice. And then there's a third crate that contains the QPAC and HTTP3 stuff. So if you need it, you can pull it in. If you don't, you can leave it out and do something else. So Russell's and Ring, as I mentioned, I'm really happy with that. If you're using something else for your TLS today, consider doing this instead. It's likely to be more secure than your OpenSSL, maybe more secure than your secure transport. I think so far Ring and Russell's have proven to be not vulnerable to all the OpenSSL vulnerabilities that came out. So that speaks for something, I think. And Russell's, again, is fully in safe Rust, just stable Rust. Ring, there's some unstable, and ASM, of course, for performance you need it, and for security and side channel resistance you also need it. But these are some really capable maintainers doing that stuff, and you could do much worse than rely on them, I think. So what we did is put all the necessary stuff in there that we needed for QUIC. And that was quite a bit of work, because if you're not familiar with TLS implementations, just to go in there and change how they do handshaking can be a little tricky and can take a lot of time. But yeah, we learned from that, and it's now all in there for you to also use. And yeah, there's a TLS interface. So really, what QUIC, the transport, because QUIC has this transport and TLS really separate, there also has to be an interface between the two, and the interface is not so specific to TLS as implemented. So, for example, you might have heard of noise, the cryptographic protocol, and that's a contender for at some point being a simpler and possibly therefore more secure replacement for TLS in the context of QUIC. And actually, at some point, some groups, the NCC group and the cryptography group at Cloudflare, already implemented using Quinn as an example. They plugged in a noise-based crypto protocol, and they were able to make that work and show that it was actually faster. So that was really interesting use of our code. But so yeah, you don't have to, at some point we might not use TLS, we might use something different, or your application might want to use something different. And then you just implement this. I don't know if everyone can read it, but it's fairly straightforward way to get going. And so I have been working on this, so because while I think Russell's and Ring are great, there are people who really want to be using the OS native stack. And so while we don't have support for that, we do have a tradified crypto session. So if you need that, then you can sort of plug in your impl for another SSL stack. But you'll still need to do all the work to do custom handshaking and transport parameter extension. But hopefully this way it's much easier to plug in than it would be otherwise. Yeah, we took some inspiration from H2, of course. H2 is the implementation from Sean of Hyperfame and Carl of Tokyo Frame. And it's a really good implementation. And they use it for Linkerd, so it's quite battle tested, I think, especially in terms of performance. So we looked at it quite a bit for inspiration because, of course, it's very similar, and we make sure that we steal all the best ideas for how we implement H3. And actually, recently, Carl asked me, could Quinn eventually become offered as a part of Tokyo? And that, of course, is something that we would really like to do. So maybe at some point we will offer, or QUIC will be offered as part of Tokyo natively, and it will likely be Quinn that offers the implementation there. It's been really good to work in the Rust ecosystem. So we have had a bunch of other people that contributed smaller things to Quinn, and we've worked with these other libraries that I mentioned already, Ring and Russell's, but also libc, where we implemented the ECN support, and Tokyo, where we worked on a implementation of timers. You have the delay type, where you can do futures-based timers, sort of timeouts. Now, QUIC really needs a lot of timers and timeouts, as you might imagine. So the delay queue is a way to have many different kinds of timeouts, all being tracked off in a single sort of type in an efficient way. And that was contributed to Tokyo, and we made some bug fixes after that. And of course, Quinn also depends on a great number of libraries, and all really, we find that the ecosystem provides pretty much all that we need. So where we are today is that we have this very conformant draft 18 implementation. We did some very early benchmarking, which shows that it's not great performing, but that's because we haven't optimized at all. And there are some easy low-hanging fruit wins in there. We have a complete QPAC implementation contributed by some very cool French contributors. And one of them should also be working on H3, but that's not there yet. We have an async await based implementation on a nightly branch, so that we were able to verify that that will work, and that will simplify our implementation considerably. And it seems like the pace in transport and TLS drafts is now slowing down, so the core of QUIC is stabilizing fairly okay now. It's more on the HTTP3 level that we will see further development that we'll have to track. Some open projects. So H3, as I mentioned, I'm working on a project right now where I'm doing a task per connection. So right now we have to run a single endpoint on a single thread, because the way we implemented it at first is that the endpoint owns all the connections. That's of course not very scalable. At some point you really want one connection per thread or per task so that you can dispatch over the thread pool. So I'm in the process of untangling all that, and that's going quite well. When that's done, I want to finish the pluggable TLS so that it's really exposed as a type parameter. And then some other open projects are stream prioritization. It looks like some people will need that. So the first users are also coming out of the woodwork. And MTU discovery, so this is where once you start it up and you can use only a minimal MTU that's guaranteed, and then you try to ping your peer to see basically whether you can put larger packets in there, which makes it more efficient. There's one other Rust implementation that I wanted to mention. This was done by Cloudflare. I found it a bit disappointing that they started another one instead of working with us, but that's the way it goes sometimes. They had a C++ version originally, but at some point they felt that it was growing too complex and that Rust was perhaps promising. So they released this to quite a bit of fanfare recently. It is sort of comparable to our Quinn Proto crate, but it's even a bit more low level, I think. It's really written to be slotted into a C API, and it uses the boring SSL bindings that they use throughout their network stack. So that's a different choice than we made. I think it's they've got a few people working on it full time, so that's nice, but it's a different thing. So yeah, come help us out, because we can also always use more people that help move this piece forward, so that by the time the QUIC and HTTP3 RFCs roll around, we have in Rust something that we can work with and actually deploy. That's my goal to have, and I hope that other people are also interested in getting that. And that is all I have. Any questions left?
So it's clear that H3 will help a lot when you have like a bad connection, because it uses UP and you don't have that. But do you expect it to perform better as well in a context where the network is really good, like in a data center, for example?
Yes. So the handshake, I mean, there are a bunch of places. So the handshake is leaner, faster, and uses fewer round trips. It also supports 0 RTT, so you can do idempotent first data submissions, because there's the risk of replay attacks for 0 RTT data, but that is supported. Otherwise, it's probably, there's not a big difference. I think there's also always still the question of all this quick machinery versus the very optimized in-kernel implementations. So there's a question how that will play out. I don't know. We're also seeing that QUIC can be, or will be, a bit more memory intensive probably, because of all the tracking that it does. But it remains to be seen, and all of this is not optimized, right? It's in that sense much earlier than it is for TCP, so it will remain to be seen, I think. But I don't think there are any conceptual reasons that it will be much faster, but there's probably a few things where it's a little faster. Anything else?
And all your socket code, that's all in the async grid, right?
Yeah, so right now we just use the Tokyo UDP socket type, and you can put it in an endpoint type, and then it goes off to the races.
Okay.
Yeah. That's all.
Do you know of any frameworks that are going to implement QUIC anytime soon?
Well, so ideally, we would put native support in Hyper to do, I think they call it alt service negotiation. So this is where at the HTTP level you can advertise that H3 is available. I think you can also advertise it through LPAN, so the TLS level protocol negotiation. So there are a bunch of ways you can advertise that it's available, and the same as I think Hyper today can upgrade from HTTP1 to HTTP2. Ideally, we would also do that for HTTP3. So in that case, you could get it for free under some circumstances. For example, you'd have to be using Russell's, because otherwise it probably will be a bit tricky. But so I'm hoping at least that it will be possible to, in these sort of common cases where you're just using HTTP, or where you and where you control both the server and the client, or where the other side already supports everything that you need, there will be ways to negotiate yourself to automatically opting in to H3.
And on the other side, browser support. Chrome is probably going to support it, but H5.
Chrome and Firefox and Safari are all in that matrix. So they're all working on implementations. I suspect that similar to TLS 1.3, by the time the RFC gets published, it will be days or weeks before they turn it on, at least in some part of their population.
So Firefox already has their CSS rendering engine in Rust?
Yes.
So do you know why they chose to make their own, probably non-Rust?
I pushed back a bit on that with the Mozilla folks, and ultimately it seems like the forward-looking people are not in the networking group. So the networking group, formerly it was Patrick McManus, and he worked on his QUIC C++ thing, and today it's a lady who succeeded him when he left for Fastly, and she was not very interested in doing this. But it was also, there was some hesitation about we're using Russells, and we also hadn't very clearly pitched. Well, I tried to pitch this separation between Quinn Proto and Quinn, because I think potentially for a project like Firefox, where you have to slot into a big C++ code base, that could be interesting, but they didn't really seem eager. And I talked to EKR a little bit, who is the Mozilla CTO and also one of the big players in the QUIC standardization and TLS. He didn't really thought it was important enough to overrule his folks. Fair enough. So yeah, I tried to get them to adopt and play along with us, but that was not successful. Similarly, I tried to get the Cloudflare folks to play along with us instead of diverging into their own land. That was also not successful, but yeah. Okay. Anything else? Okay, thanks.